the next speaker is Julian, which is the initiator and the tech lead of a project Firefly, which is what you are going to hear in the presentation at Google. Julian is currently focusing on building new application and system capabilities enabled by precisely synchronized clocks. He is one of the recipients of a SIGCOMM' Doctoral Dissertation Award in 2020. The stage is yours.
Thanks for the introduction. Hi, everyone. I'm really excited to introduce Firefly, a clock synchronization system for data centers that is highly scalable and ultra accurate. As I will soon show that achieving either high scalability or ultra accuracy is challenging, and the Firefly achieves both. So let's start with the trend. There is a demand for clock accuracy that is growing tighter. Starting from tens of years ago, we have NTP that has millisecond accuracy. And as we move to cloud computing and a high-performance data center, we start to see applications that demand sub-millisecond, microsecond, or even sub-microsecond accuracy. And with new applications such as financial exchange, it started to ask for sub-10 nanosecond accuracy. And this is because in financial exchange, the fairness is the top priority. Imagine when the market starts to broadcast data to all the participants. We definitely want all the data to arrive to all the participants at the same time. We don't want someone to get data earlier than others, right? That's very unfair. So to achieve this and monitor this, we need sub-10 nanosecond accuracy. And this is just one of the many examples that require clock synchronization. The sub-10 nanosecond accuracy actually brings a huge challenge. So let me start from the building block of clock synchronization, which is measuring the offset between a pair of clock, A and B. That's typically achieved by sending a pair of packets between A and B, from A to B and B to A. And each packet can give an estimate of the offset. For example, the receive time B minus the transmit time at A minus the one-way delay from A to B is the offset between A and B, given by the first packet. And the second packet also gave a similar estimation. If the one-way delay from A to B and B to A are equal, then we can add these two equations up and get a simple calculation of the offset between the two clocks. And we can visualize this. Since the offset is the sum of these two divided by 2, the offset is actually the middle line between the blue term and the orange term. So here we draw the time series of how the offset evolves over time. So this is the ideal case. And of course, in practice, the delay in the two directions are not the same. They are asymmetric. This is because the packet going in the forward direction and in reverse direction can take a different path. And different paths have different cable lengths that can introduce hundreds of nanosecond difference. So in financial world, the typical solution is to use equal length cable. But even with equal length cable, the difference can still be tens of nanoseconds, much higher than our target. This is because the cable cutting itself has some error tolerance, so that they are not exactly the same. Besides, when we are targeting sub-10 nanosecond, we start to care about the asymmetry inside individual components. For example, an optical transceiver, the delay in the one direction and in the other direction can differ by up to 5 nanoseconds. And this adds up every hop. In addition to the asymmetry, the jitter also becomes more challenging to handle. One of the common sources is the queuing jitter, which can be a microsecond level. And one way to mitigate it is to use strict prioritization. But strict prioritization still leaves tens to hundreds of nanosecond jitter because it can bypass the queue, but it cannot preempt the packet that is already transmitting. And in addition, we have to care about the hardware timestamping jitter, which is 10 nanosecond level, because we are targeting sub-10 nanosecond accuracy. The drift also becomes more challenging because, so typically the static drift is the major source of drift, but it's relatively easy to correct. But when we are targeting sub-10 nanoseconds, the dynamic drift becomes more challenging because it makes the curve of the offset start to become curvy, right? So offset measurements soon become obsolete, so we have to do it frequently. These three different error sources, asymmetry, jitter, and drift, they are common to any pair of clock offset measurement. And there is one special node in a cluster called time server that serves as the source of time to the entire cluster. And this time server itself has much higher error than the target. This is understandable because it has a special job. It has to take time from the satellite to the antenna, then transfer time to the atomic clock, to the CPU, then to NIC over PCIe. And this PCIe jitter can introduce microsecond level of jitter. Then eventually the time goes to the rest of data center. How can we achieve sub-10 nanosecond accuracy with the source of time itself has much higher error? And thirdly, the scalability becomes much more challenging because of so many more factors that start to emerge, as I mentioned before. And we have to react to these events much sooner because of the sub-10 nanosecond accuracy. Existing solutions typically use a centralized architecture, right? All the nodes talk to a centralized component. So they are limited. Their accuracy is limited by the scalability of the centralized component. And it's also a single point of failure. To try to scale, right? Some solutions use tree architecture, but that is more vulnerable to the nodes in the middle level. If some node in the middle level is drifting or even misbehaving, it can lead the whole subtree astray. So these are the three key challenges, right? We start to care about new error sources that previously we typically ignore when we are targeting sub-10 nanosecond accuracy. The time server itself, right, the source of time itself has more error than the target. And the scalability becomes more challenging. So how does Firefly address all these challenges? Instead of keep optimizing existing solutions, we take a different direction. At its core, we use distributed clock consensus to achieve clock synchronization. That is, each clock talks to multiple other clocks in the same cluster and converge to the average of them. In this way, all the clocks will converge, will achieve a consensus of time. This provides another level of error reduction on top of all the existing approaches because it can average out independent errors across multiple clocks. And equally important is that it is highly scalable in that the larger the scale is, the more clock we have, the more stable the consensus is. So essentially, we employ the scale in favor of clock sync instead of fighting against it. We also have theoretical foundation for the distributed consensus. We have proof that when running over a d-regular random graph, right, meaning every clock talks to d other randomly picked clocks, it is highly scalable. D only scale as O log n, where n is the size of the cluster, to achieve the same level of accuracy. The consensus also converges fastest over the d-regular random graph with high accuracy and a bound on the static error. The second key design is called layered synchronization, where we decouple the consensus from the time server error. I will talk about detail later. And the third key design is software-driven error mitigation that further filter out the past asymmetry and queuing jitter. So as I've talked, the consensus runs on a random graph, which is overlaid on top of the physical network. So the NICs that are talking with each other can be actually many hops away, can be distant in the physical network. Here I use the NIC as an example, but actually anyone can also run Firefly on the switch to synchronize switch clocks if they want. And here's the overview of the synchronization process. It has two layers of synchronization. The first layer is called internal sync, where the distributed consensus brings all the NIC clocks close to each other. Right? Initially, they are spread out, and the internal sink brings them very closely. The external sink is layered on top of the internal sink that moves the consensus as an entirety towards the time server. Now let me deep dive into the Firefly techniques. The distributed consensus provides another level of error reduction because it can average out errors from multiple other clocks. When one clock only talks to another clock, right, you get one curve like the one dashed line there. But when you talk to multiple other clocks and take a consensus of them, it averages out the errors that are mostly independent. The distributed consensus is also highly scalable. As we mentioned before, it scales as O log n to achieve the same level of accuracy, but equally important, it also scales in a fault-tolerant way. This is because any node that is drifting or even misbehaving can be easily detected when comparing with all the multiple clocks being synchronized and easily filtered out. It's also highly resilient to failures because it has many peers to sync. So this means the larger the cluster is, the more stable the consensus is, both in terms of accuracy and in terms of the fault tolerance. This in turn helps the accuracy. I will talk later. The second technique is called layered synchronization that shields the time server error from affecting the NIC-to-NIC accuracy. We designed the external sink to be gentler than the internal sink so that the consensus themselves moves as an entirety towards the time server without being affected by the large error from the time server. This gentler external sink also improves the UTC accuracy. Right? This is because this gentler external sink is effectively tracking the long-term average of the time server. So the green line here is the consensus, right? The red line here is the time server. The green line, by tracking the long-term average, is actually closer to the UTC. And this is achievable also because the consensus is highly stable. So it tracks the highly stable UTC. It can easily filter out the error in the middle from the time server. And lastly, we also have software-driven techniques to filter out asymmetry and jitter coming from the path and the queuing. So in every pairwise measurement, it can have its own asymmetry and jitter, and that is the input to the consensus. So by improving this quality of this measurement, we also improve accuracy. You can refer to the paper for more details. So with all these techniques, can Firefly achieve sub-10 nanosecond accuracy? The answer is yes, but it actually took us a long journey to actually measure the accuracy of Firefly. This is because a typical challenge in clock sync is that the measurement itself has to be more precise than the synchronization system itself. And that means we need a specialized hardware to measure it, and which is hard to scale. So in order to evaluate Firefly, we built a test bed. It's a standard Jupyter network, right, with more than 200 NICs. But importantly, we use one oscilloscope connect to 7 NICs using 1 PPS that serve as the ground truth to measure the accuracy. And separately, we also use another special device called Ixia that connects to 60 NICs to measure the accuracy. The Ixia has slightly higher error, but it can measure more NICs. So let's first look at a dashboard from the oscilloscope. Oops, you did. Yeah, sorry for the noise. It's taken from a data center. Yeah, but you can see that all the clocks, right? Each row is a clock. They are well aligned within a couple of nanoseconds. This is 10 nanoseconds, this is 0. So they are well aligned within a couple of nanoseconds. And we summarize the measurements in a graph, right? On the left, we show the CDF across all the NICs being measured. And on the right, it's a time series of one example pair of clock. And it shows Firefly achieved under 5 nanosecond accuracy across the Jupyter network. We also use XCR to measure the accuracy at scale, right, across the 60 NICs. But before that, we use 1 PPS to validate the XCR measurement. These two plots shows the same set of NIC being measured by both 1 PPS and the XCR. The XCR measurement itself does have some additional error, so it actually overestimates the error of Firefly. And that's a trade-off we have to pay for measuring more NICs. But yet, the XCR still reports under 10 nanosecond accuracy at P99. I'd encourage everyone to read more in the paper, which shows Firefly is more accurate and highly scalable and resilient to larger errors and failures. In conclusion, Firefly delivers sub-10 nanosecond accuracy with distributed consensus, layered synchronization, and software-driven techniques. We also provide theoretical foundation in scalability and its accuracy. And finally, I want to say that with Firefly, it actually transforms our view of data center from a set of loosely connected machines to a tightly integrated computing entity where things can be easily scheduled and coordinated. With this, we believe we can enable more applications that can be more efficient, more performant, and more scalable. And with this, I'm happy to take any questions.
Thank you very much. Any question?
Shall I go first? Okay. Thanks for the talk. Quick question. How does your accuracy depend on the link latencies? And in particular, for example, could a similar solution be used in cellular networks which require synchronization across base stations, or maybe multi-region network where maybe the latency between two links is longer? Or will it only work under some conditions on the link latency?
Sorry, can you repeat and speak slower?
So I guess your accuracy may depend on the latency of each link, right? Or of the round-trip time across each link. So are your nodes all in the same data center or in the same rack, or can they be across multiple racks? And then how does your accuracy depend on this, on the link latency?
Yeah, that's a great question. So in our evaluation, the accuracy is across the entire data center, right? It's a Jupyter network with 6 hops away. As for your another question where the accuracy depends on the latency, it actually doesn't depend directly on the latency, right? Because in this calculation of the offset, you can see that the offset is just using the 4 timestamps, right? It doesn't really depend on the latency of the network.
Can you use servers from different data center, one on the East Coast, one on the West Coast?
Yeah, so you're asking about cross data center, right? Even cross regions.
Well, that's a latency, larger latency, right?
Yeah, I think that is the next level step we are going to explore. There are some new challenges, right? There are more, even higher jitter, right? Even packet loss in there. So that has unique challenges.
Okay, thanks.
Thank you for your presentation. Impressive work. My question is actually somewhat similar to what he asked, because you used the exchange problem as a motivation example, but then your evaluation results is I think within the same data center at least. Would there be any limitations in applying this to, for example, the exchange scenario where different entities own their own networks, and you don't really have ownership over the entire network? Because data centers are owned by the same company, right? So you can probably do something there, path selection, whatever. What if there are multiple entities that are trying to sync clocks and they each own a subset of the network?
Yeah, in exchange, typically the participants connect to the same network and get time synchronization from that provider. That's what typically being done. So, and for your question, how to, if there are different entities, they try to synchronize, right? They may run different protocols. They may not trust each other. So I think that's a really great question to explore, right? In such a competitive environment, how do we ensure a fair and accurate market? Yeah.
So I have a couple of questions about I'm over here, by the way. I've got a couple of questions about the uses or the potential additional uses that you could put this to once you have such precise synchronization within the data center. For example, you could imagine it providing a service to the infrastructure itself in consistent updates, lossless updates, state updates within the infrastructure and the network and the systems as a whole. Accurate measurement of one-way delay, which is helpful for many algorithms. So I'm kind of curious, beyond the example that you gave, which was financial transactions, are you anticipating using this for throughout the infrastructure?
Yeah, definitely, yeah. Beyond the financial exchange, I think several things in my mind. First is, of course, building the next generation of financial exchange, right? We know today's financial exchange is using highly customized fabric network, equivalence cables, but with clock synchronization, we don't need all of those. I also have some other examples in my mind. For example, we can schedule traffic ahead of time, right? Especially like in machine learning tasks, right? We can avoid all those congestion, all those packet loss, and achieve high performance. And also in in database, we can rethink how we design database, how we design those concurrency control protocols, because all existing protocols, they somehow implicitly assume the clocks are not that accurate or not that reliable. But this is a very new assumption that can shift the way people think about database.
Okay, then we don't have any more time. Thank you again.